the lecture series on mathematical modeling and analysis. In the last lecture, we have discussed this phase diagrams and the null Klein functions for nonlinear differential equations. And in the present lecture, we will discuss about continuous time Lotka Volterra competition model. So, especially in this model, we will just use like two species which can just compete each other for the resource of food, or like the same species or like other species can be present there over for they can just compete for like different resources or a different source of foods. So, second phase we will just go for this Lotka Volterra competition model, since this scientists like Lotka and Volterra, they have discussed this model for two species model, when there is like two species are present and they can just compete for the same resources. So, if you will just go for this competition model, if instead of one species in a population, if there are like two or more than two types of species are introduced simultaneously into the same culture, then the growth of one species can be hampered by the extent of this nutrients or habitat that are shared by other type of species. This type of interaction is known as like a competition model here. The competition may be like interspecific between two or more different species, or intraspecific, means like inside that population they can just like struggle each other to get the food. So, between members of the same species especially it can be said to be. Sometimes only the strongest species prevails, making weaker species to decline, and this is called principle of competitive exclusion. Since if somebody is stronger, they can just get the food, and weaker they cannot survive in that situation. The competition models were first given by Alfred James Lotka. He is a USA mathematician and a physical chemist, and this Volterra, who is an Italian mathematician. So, independently they have just given their model, and if you will just go for this Lotka Volterra competition model. So, a simple logistic model if you will just consider, that is in the form of like dn by dt, this equals to Rn into 1 minus n by k, which can be especially written as Rn into k minus n by k, where R represents the intrinsic growth rate and k is the maximum carrying capacity here. So, if we will just consider an Iceland where only two types of species are living, the corresponding model will be given by like dn1 by dt, where a intrinsic growth rate it will present, that is corresponding to this like atmospheric condition or like resources available. This population level with respect to time will get changed, that is especially R1 n we have just tried, and then this population level it will be controlled by different factors. So, first one it is some other species or certain other constants if it is or constraints if it is present there. Then it will be declined by the other species if they are present over there. That is why we have just written here minus beta 1 to n 2. Similarly, if a second species it is just present over there, that rate of change of that population, which can be written as R2 as the intrinsic growth rate, N2 is the total population level, and which can be affected by like the total population level N2 with the presence of like fast species whatever it is just present in that population level. So, that we have just explained it in a clear form here if you will just see. So, beta 1 2 we have just written here, that affects on carrying capacity of fast species due to individual of second species present there, and beta 2 1 that affects the carrying capacity of second species due to the presence of fast species there. So, that is why beta 1 to n 2 that restricts the total effect on carrying capacity of fast species due to the second, or in layman we can just say that the amount by which growth rate of fast was affected will be declined due to the presence of second. Same it can be applied for like N2 population there. And if you will just consider here like this constants beta 1 2 and beta 2 1 equals to 0 here, then it means that one of the species that will not be affected by the other species there. But you can have a competition model, since inside the population there will be some weaker elements and some are stronger elements present there. they will just compete each other for the food or resources there. So, that is why still a competition will exist between these individual species there. And the system, if you will just see here, the equation represented in 19.2 here. So, which represents a two nonlinear first order first degree differential equation. And if we want to go for the steady state here, then we can just write this one as like n1 into k1 minus n1 minus beta 1 to n2, this equals to 0, and also n2 into k2 minus n2 minus beta 2 1 n1 by k2, this equals to 0 here. So, this will just give you like n1 equals to 0 or n1 plus beta 1 2 plus n2, this equals to k1. Similarly, n2 equals to 0 from the second equation, and beta 2 1 n1 plus n2 equals to k2 here. So, the steady states are like 0 0. If you just put n1 equals to 0, we can just find k2 equals to 0 also. So, if you just put like k1 equals to 0, then we will have like k2 n2 equals to k2 here, and if you just put like n1 equals to k2, then we will have like k2 equals to 0, and another equilibrium point that is just occurring at k1 minus beta 1 2 by k2 by 1 minus beta 1 2 beta 2 1 k2 minus beta 2 1 k1 by 1 minus beta 2 1 into beta 1 2. So, we will have like 4 equilibrium points now. So, this steady state 0 0, this represents that no species is present at that level, or this represents the absence of both the species. So, if both the species are absent, so the population cannot grow in that level. Second one is like a k1 0, this represents that the first species is present, second species is absent. 0 k2 represents that first species is absent, second species is present with maximum carrying capacity. And the fourth one, which is represented as k1 by beta 1 to k2 by 1 minus beta 1 to beta 2 1, and k2 minus beta 2 1 k1 by 1 minus beta 1 to beta 2 1, which represents both the species are coexisting at that level. So, if you just go for null clients here to find the stability or instability situations. So, there are 4 possibilities if you just see here. So, first possibility is that if you just see here, so k2 minus beta 2 1 k1 if you just consider here. So, this means that k2 by beta 2 1 either it is greater than k1 or it is less than k1. Based on that, we have just considered like 4 conditions here. First condition is that k2 by beta 2 1 greater than k1 and k2 is greater than k1 beta 1 2. Only these conditions we are just assuming here. And second condition, if like both these are like less here, this means that k2 by beta 2 1 it is less than k1, and k1 by beta 1 2 it is like greater than k2 here. Similarly, 1 by 1 this like sign changes we have just considered are like different cases here. So, in this case we have just considered like the first case only it is the reverse process here, k1 is greater than k2 by beta 2 1, and k2 the same one we have just considered here. Similarly, in this fourth case we have just considered this one as like k2 by beta 2 1 as it is greater than k1, and second one remain the same. So, based on these 4 conditions, if you just plot the graphs here, for case 1 we can just find that we will have like k1, since k1 is less than k2 by beta 2 1. So, k2 by beta 2 1 we have just considered it is the larger point here. Similarly, if you just put here k2 is greater than k1 by beta 1 2. So, that is why we have just joined all these points here to establish this relationship. And we will have this axis that is as a n1 axis and n2 axis. Similarly, we have plotted for like case 2, case 3 and case 4 here. And for the like case 3, we are just getting that whenever like k1 is greater than k2 by beta 2 1 here. So, we will have like k2 by beta 2 1 it is less than k1, and k2 it is like larger than k1 by beta 1 2 here. If we are just connecting these 2 points, that is k1 and k1 beta 2. So, there is a intersection of these lines or these null lines here. So, if we will just go for like further analysis of these points, we can just find that whenever k2 by beta 2 1 is greater than k1 and k2 is greater than k1 by beta 1 2 here, there are only 3 steady states here. First one is a 0 0 here, second one is a 0 k2, third one is like k1 0 here. And for the 0 0, if you will just see that these null lines of n1 and n2, they are just intersecting each other. Since we have just considered that different null lines should intersect each other to get the steady state points. And 0 k2, if you will just see here, that is nothing but intersection of n1 equals to 0 and beta 2 1 n1 plus n2 equals to k2 line. Similarly, if you will just see this k1 0 line here, that is nothing but intersection of n2 axis and n1 plus beta 1 to n2, this equals to k1 axis here. So, from the biological point of view, if you will just see steady state 0 0 cannot be stable, because it is stable, it means that both the species will extinct after certain time. So, if both will dies out in that situation, that cannot be a stable position. So, this is not the practical case, because species are just competing each other for food, not killing each other. They will just survive each other, whatever the resources it will be available. So, some species they can eat and they can survive instant or any type of situation. So, that is why we cannot say that this 0 0 point is a stable point here. And if you will just see this k2 point here, if you will just consider any like point above this k2 or below this k2, always we can just find that this level or whatever the point we can just choose, that will just move towards k2, and since this will just give you like increasing function there. So, towards the point k2 there, and if you will find any like values which is above this k2, that will just coming towards the point k2. So, that is why this k2 is a stable point in that scenario. And the same thing we can just we cannot observe that at k1 point, since if you just put any value here k2 by beta 2 1, if you will just see here. So, k2 by beta 2 1, it is always larger than k1. So, this means that whenever this population of k2, it will be larger compared to the first population. So, then they can just use this food, and we cannot find a like stable condition at k1 level also. So, if you will just go for this further analysis of this model here, steady state 0 k2 and k1 0 may be stable individually, if you will just see here, but not simultaneously. Since this shows that one of the species will dominate other and make other two extinct there. This means that one will survive and other will just dies out in that scenario. So, if you just see this graphs here, whenever k2 is a stable point here, this means that either we can just consider either k2 or k1 here. Since there is no intersection of two non-trivial non-lines for this case here, it means both these species will not exist together. And if we will just analyze this test case for the point 0 0 here, at point P n1 dash equals to 0 to get this null line lines, and n2 dash equals to 0, which means that both n1 and n2 remain constant, hence are not stable also. So, that is why we are just pointing this arrow in both these away from the both these directions. So, this means that this is just going there and this is just going in the outward directions, since n1 dash and n2 dash both are n1 is constant and n2 equals to constant there. And the remaining arrows can be drawn easily by using the fact that whenever nature of arrow changes only at the intersection of two null lines. And so, by null line phase diagram we can conclude that steady state 0 0 and k1 0 is unstable, while 0 k2 is stable here, only second species will exist. And if you will just go for like for the second case here, so when k1 is larger than k2 by beta 2 1 and k1 by beta 1 2 is greater than k2 here, we can just plot these lines. So, first if you will just see here 0 0, it will just intersection of n1 and n2 axes, and 0 k2, that is nothing but this line here. So, this is intersection of n1 equals to 0, and the second line, that is beta 2 1 n1 plus n2 equals to k2. Since if n1 equals to 0, obviously k2 equals to n2 there. And third point, it is k1 0, which is intersection of this n2 equals to 0. If n2 equals to 0, we will have n1 equals to k1. And for this case, we can just find that k1 represents the stable state here, but K2 it is unstable, and there is no intersection of non-clients also here. So, for the test point, if you just consider as p equals to 0 0, if you just proceed like our earlier case, whatever we have just considered here. So, we will have n1 dash equals to 0 and n2 dash equals to 0. This means that n1 and n2 will remain constant, hence not stable. So, always if the food is or the resources it is utilized by both the spaces, they cannot be constant, since either food resources will just goes down and one species will compete with the other, and one will be declined and other will like survive there over, or further we can just say that one will like grow up, other will just decline there. And the null client diagram shows that if you just see here at different levels, so we can just find that K1 0, if you just put in the equation, we can just find that it is just represents a stable state, while 0 0 and K2 0 K2 are unstable. So, first species will exist in this case. Third case, if you just consider like K1 is greater than K2 by beta 2 1 here, and K2 is larger than K1 by beta 1 2, we will have this like equilibrium points 0 0, 0 K2, K1 0, and we can just find that the fourth point that is existing as K1 minus beta 1 2 K2 by 1 by beta 1 2 beta 2 1, K2 by minus beta 2 1 K1 by 1 minus beta 1 2 beta 2 1. That is the intersection of these lines, which is just drawn from like K2 2 K2 by beta 2 1 and K1 by beta 1 2 to K1 here. Since the intersection of null clients it is just present there, so it is just give you this steady state condition. And if you will just analyze, this will just give you also a like a intersection point which is represented by this value here. And in this case, two species cannot coexist because the steady state, this one it is not stable. If you just see here, all the values they are just going downwards, and for this axis we are just finding that all the values they are going outwards also. And in the above of this line, if you just see, this is just pointing towards this n2 axis, and in the like in the leftward direction, and if you just see below these points, they are just pointing towards this like away from this 0 0 point. So, that is why this will not give you a steady state. Individually, if you just see here, so we can just find that both these species are stable, but not coexisting together here. Since K2 level we are just finding a stable point here, and like K1 level we have also obtained a stable point here. So, individually both the steady states 0 K2 and 0 K1 sorry K1 0 are stable, but no coexisting together. And if you just go for like case 4 here, there are like 4 steady states, especially if you just see, since there is a intersection of these two null clients is existing here. So, we will have these points 0 0, 0 K2, K1 0, and this coexisting condition. And in this case, two species can coexist because the steady state this one is stable here. Since if you just see above this line points are pointing towards like to the axis there, n1 axis, and if you just see here the points which is existing below this line, they are also pointing towards this stable point which is existing for like a coexisting of both this population level. Hence, this represents a stable condition. Since both are existing or coexisting together, so individually they cannot achieve a steady state. So, further we will just go for like Lotka Volterra competition model, that is we will just do this like Jacobian matrix analysis here. So, if you just consider this Lotka Volterra competition model, which can be written, since already we have written that one, that is in the form of dn1 by dt. This is written as r1 n1 into k1 minus n1 minus beta 1 to n2 by k1, and dn2 by dt, which is written as like r2 n2 into k2 minus n2 minus beta 2 1 n1 by k2 here. And if you will just put this one, this equals to 0, this equals to 0, we can just find the steady state conditions. But first order differentiation with respect to n1, if you just do, that will just give you this first term here, and if you will just do this like differentiation with respect to n2, that will just provide this term here, and if you will just go for like a first order differentiation of n1 of this equation here, then we will just get it as like minus r2 k2 r2 by k2 n2 beta 2 1. So, similarly we can just get after like a differentiation with respect to n2, we will have like r2 by k2 k2 minus 2 n2 minus beta 2 1 n1 here. So, this is nothing but the like differentiation with respect to d by dn1 for the first function we are just doing this one. If I will just write this as like f n1 n2 here, this is like g of n1 n2 here. So, then we are just differentiating this one f here, this is a d by dn2 of f here, this is a d by dn1 of g here, this is a d by dn2 of g here. So, then at the steady state 0 0 we will have this Jacobian value. If you will just see here n1 n2, if you will just put 0, then we can just find these values as like first value as r1 here, then 0 and r2. If you will just see, since k1 it will just cancel it out here, n1 n2 is 0. So, that is why this is just coming as r1 here. So, here n1 is 0, so n2 is 0 here also. So, same thing here, that is r2 by k2 into k2 here. So, both these quantities are 0. So, that is why this is just coming as r2 here. And Jacobian J1 is nothing but the diagonal matrix here. So, we will have these eigenvalues, that is nothing but the diagonal entries here r1 and r2, both are positive. So, the steady state 0 0 is unstable here, and we can just compare this result with the null lines in the all the 4 cases, you can just see. So, for steady state 0 k2, if you just see the Jacobian matrix is just given these values. If you just directly put n1 equals to 0 and n2 equals to k2, we can just obtain this Jacobian here. And if you just go for the analysis of this Lotka Volterra competition model in this like eigenvalues analysis here, Jacobian J2, if you just see here, is a lower triangular matrix. So, these diagonal entries are nothing but the eigenvalues here. And if you just see one of the eigenvalues minus r2 is always negative, hence the stability of the steady state will be entirely depend on the nature of the eigenvalue r1 into k1 minus beta 1 to k2 here. So, when if we can just assume here k1 is less than beta 1 to k2 or k1 by beta 1 to less than k2, the eigenvalue will be negative and will make the steady state 0 k2 is stable. This means that we just try to compare this both these methods for this Lotka Volterra competition model here. And for steady state k1 0, we will have this Jacobian, that is in the form of this here. And if you just see here, J3 is an upper triangular matrix and the eigenvalues are nothing but we can just take the principal diagonal elements here. So, the stability region, if you just see here, we can just find k1 0 will turn out to be k2 by beta 2 1, it is less than k1. We can just compare this one with the results of null lines also. Similarly, if you just go for like for steady state at this point, Jacobian will be given as this one here, and for this we have to do like lot of algebraic works to find the eigenvalues for this Jacobian here, and we have to skip all these calculations since it is a tedious task here. Since the primary goal is to analyze the calculations here, after solving the stability region of steady state here, we will just get that different regions we can just define here. K2 by beta 2 1 is greater than K1, K1 by beta 1 2 is greater than K2, which is same for the inequality, it is considered in case 4 for this null lines we have just considered. And till so far we have studied this null line behavior and Jacobian of Lotka Volterra competition model. Now we can just proceed for actual phase plane diagram with help of null line and Jacobian. So, manually it is difficult to draw the phase diagram. So, we will just analyze them together to get a clear overview of this model. If you will just see for the first model here, we can just find that in Jacobian sense that if we are just finding here R1 and R2 are both are positive. So, the steady state 0 0 is unstable. we can just say that 0 0 is an unstable point here. Second analysis, if you just do here, like for 0 k2, we have obtained that one of this eigenvalue, that is 0 k2 is stable, since we will have like k1 is less than beta 1 to k2 and k1 by beta 1 2 is less than k2. The same thing we have just considered for this case also. So, that is why we have just find that k2 is a stable point for this case. And point wise analysis, if we can just do these arrows, if you just visualize in case of null lines here. We can just find that k2 is also a stable point. If you just put all these arrows in line form there, that lines are nothing but if you will just see here, these are the lines here, which is just pointing towards the point k2 here. So, for the second case, if you will just see here, then we have just obtained in Jacobian model k1 as the stable point here, k1 0. If you will just see, the stability region k1 0 will turn out to be k2 by beta 1 is less than k1. The same thing we have obtained for this Jacobian as well as null lines for this case also. Similarly, we have analyzed the stable state for like third case, that is k1 is greater than k2 by beta 2 1 and k2 greater than k1 by beta 1 2. So, we want to visualize that both this like qualitative approach and the null lines both should be same. So, that is why this analysis has been put it over there. So, that is why for case 3 we have obtained this line analysis, whatever these arrows we have put it over there. So, always it is just pointing towards the point k2, and for this point if you will just see this points it is just moving towards this point and this is also moving towards the point, but at this level if you will just see these points are just going outward from this point. In this level we cannot say that this is a stable point here. And for case 4 we have just find that this is the stable steady state point, that is the coexisting point if you will just see, and at this level if you will just see these points are pointing outwards here, and in this level also you can just see that these points are outwards moving if you will just see this one, but at this level if you will just see all these points are pointing towards this point here. So, that is why it is just representing a stable state. So, if you will just go for this like intensity of this competition level, if you will just analyze, this means that beta 1 2 and beta 2 1 parameter, how it is just performing for this Lotka Volterra model. So, then if this parameter is less than 1, then the competition is less intense, and if it is greater than 1, if you will just see it is more intense. So, depending on this behavior, we have like 4 possible cases. First one, it is a beta 1 2, it should be greater than 1, and beta 2 1 it should be greater than 1. Second case, we have just assumed as beta 1 2 is greater than 1 and beta 2 1 is less than 1. Third case, beta 1 2 less than 1 and beta 2 1 greater than 1 and beta 1 2 is less than 1 and beta 2 1 is less than 1. So, all the possible cases we have just assumed for beta 1 2 and beta 2 1 in a coupled form. So, in the first 3 of the above cases, if you will just see, at least one of the species is aggressive, hence making them not to coexisting together. While in the last case, if you will just see here, both these parameters are less intense, making the system to reach the steady state, which can make both the species to exist together, since both these parameters are less than 1 here. And if you will observe, all these above 4 cases easily be obtained from previous inequalities 4 cases by considering same carrying capacity, that is k1 equals to k2. And in this model we have just discussed like first the competition models, where like more than one species they are just existing. Then we have discussed about Lotka Volterra competition models. So, first we have formulated the model and analyzed the model. Then we have just tried to explain the what is the biological existence of this model with the mathematical assumptions. Then we have just tried to analyze this model using null Klein functions, then this Jacobian, and tried to compare both this like null Klein functions and Jacobian with the phase plane diagrams. Then final phase we have just discussed this intensity of these competition levels. Thank you for listening this lecture.